Good afternoon, everyone. Thank you for being here. Thank you to the committee for the kind invitation. My name is Percy Venegas. I am a practitioner and a researcher using automation in various domains, specifically finance. And my background is in electronic engineering. And after a few years of practicing, as a graduate student, I studied finance at King's College and philosophy at Edinburgh. So what you will see is a little bit of this journey of working with different systems, and specifically with a methodology called genetic programming and symbolic regression. And some of the intriguing things that we have found, this research is in collaboration with Dr. Gobet. And we are using some of the ideas of Lakatos to try to understand a little bit better these intriguing things. So what we're going to cover is a good definition of symbolic regression via genetic programming, some examples from different domains. And specifically, we are going to talk about model ensembles, group of models. And then the process is going to be very visual. We are going to review a little bit about theory experiments, anomalies, and get some inspiration from Lakatos. So this will be similar to, let's call it, Lakatos inspired reasoning, as Alison would put it. It's not literal in every sense. But if we think about this in general, it's about the problem of connecting two points, right? We can do this and get different formulations, different ways to express it, and we can take formulations from these group of models and create ensembles, right? And see different things here. This is for Lakatos. I claim that the typical descriptive unit of great scientific achievement is not a isolated hypothesis, but rather a research program. And this is what ensembles are about. So basically, the ensembles in symbolic regression it's all about trees, right? We have variables, we have mathematical operators, and we have constants, and we have mathematical structure, graph, that mutate in certain ways, right? And there are certain evolutionary algorithms that are applied to have a variation. And what we have at the end is basically many models that compete based on a trade-off between the accuracy and the complexity. And complexity here means, how big are the trees, right, basically. And we're loosely saying, okay, this is in some way similar to what we will see in research programs, right? But at a strictly computational level, right? This is not human-based. It's only partly human-based because there is a human always in the loop. But in the difference with traditional research, scientific research, is that we don't begin with hypotheses that we try to disprove. The evolutionary processes creates the hypothesis itself, right? And the human is usually a domain expert in industry or some other field, applying certain rules during the process to decide how to proceed. So it's evolutionary combination regarding accuracy, simplicity, and novelty. And there were criteria that can be applied. And from all the models that we get, we can identify some that are optimal in some way. So they're either, like the lowest error with the lowest complexity, or some other criteria. Lakatos also says, the hardware is continuously protected from refutation by a vast protective veil of auxiliary hypothesis, right? And this idea of the hardware and the protective bell is prevalent in everything that we see every time that we use this technique. So an usual output is you will have here, we are predicting a value, some variable, in this case it's a financial variable, and here this is a behavioral observation. This is the usage of certain financial side. And basically we are seeing how the prediction performs across the parameter space, across different values of this variable that we are observing. And we have here, in the center, the mean of these different models. And each gray line is a model that is generated in this round. And we have basically in the ribbon a measurement of how it diverges, right? What is the divergence from this mean? So there is a stable prediction, and there is a group or predictions that are zeroing, right? But we have been thinking about this is that it's very similar to the idea of the hardware development. What are the inner workings of the method? So if we think about the problem from natural science, right? Basically throwing a ball and seeing where is the trajectory, right? How far it goes, how high it goes. We can sample a few points at the beginning, like we see here, up, and then generate models. In this case, in this round, we generated more than 700 models in just a few seconds, right? Each with different characteristics of accuracy and complexity. And from those, using some more criteria, we select the ones that we want to be in the ensemble, right? And the ensemble will have a variety of models. Diversity is important in this case, right? So each of these points is a mathematical expression. There is explanatory, and some of the models are complex and have low error. Some higher error are simple, right? And there is a reason for that we will review later. And basically, what we see at the end is this: when the modeling is constrained by the data, we see that there is clear divergence. There is a lot of consensus, and here the consensus breaks. And this is the case of extrapolation, basically generating theories. Lakatos also said that the research program has an heuristic that is a powerful problem-solving machine. And what we have seen when we compare this technique with others from machine learning is that it's indeed powerful. The process of evolution, right? And we are talking about the principle of variation and selection for in analytic complex systems. If we do the same experiment of the board, right, and we run a simple linear regression, we see basically the ball goes to the sky, right? In other modeling techniques is a little bit better in Gaussian processes, usually using Bayesian methods. We have a confidence band right around there, but it requires some prior knowledge. Here we are starting completely in a naive way, and the expert is involved doing the process later on. So this is also one of the interesting things about using evolution in this type of modeling. And not only for extrapolation, but also for interpolation, there are interesting uses. Right. So we see, if we sample only the beginning and the end of the trajectory, well, we have something like this. a lot of uncertainty. But then we can sample our points in between, and we start blocking in, right, the divergence. This is important in some industrial settings where you cannot destroy samples so easily, right? Or in social science experiments when you have very little data points. So one of the advantages of the technique is that you can work with many variables, many more variables than actual observations. So usually thousands of variables and just a few dozen observations will be enough. And both time series and non-time series models. This is basically how the runs of the generation of the evolutionary sequences look. You have, in this case, several cores of the machine, right, of the microprocessor, each running a process, and at some point, it looks like it is achieving some desired level of error, very, very low error accuracy, and something happens in the process starts again. But there's at some point some convergence, right? And again, each of these processes renders disparatory expression. And if it is desired to make it more human readable, you can select that this is basically linear kind of model, but by definition this is a non-parametric, non-linear modeling technique. So we can deal with all types of non-linear expressions. And we don't need to suppose the shape, right, of the expression. We don't need to know, a priori what are the structures. We just leave the model tells. And if we go back to here, right, thinking about the divergence, the consensus or the lack of consensus in the ensembles is providing a trust metric by default, right? We know that here we have to be careful, right? And even if this part is empirical, right? We had the first that was just theoretical extrapolation, and the one that was interpolation more empirical. Even if we do deal with empirical modeling, the important thing here is that we have these expressions that we can use to construct the statements, and that has explanatory power. And this brings us to the idea of dominant impact from variables, right? From the first presentation of the Lakatos Award, the first day, right, we learned about the importance of driver variables in medicine. This is, by the way, an example from cancer research. So basically, this is a vaccine-related experiment, and what we are seeing is how the variables are present across models, right? We can see that in this case, these two variables, 1 and 2, are present in a majority of the models. And also we can see how they are present together, like what is the prevalence. Now, this is obviously important in real life settings, right? And if we want to continue with the social sciences, right, and the natural sciences, it's important to look at things like this. Someone like Popper would probably say, well, we need independent evidence, right? So if we want to look at this in this way, we will actually look for the variables that are not together too much, but maybe also have some exploratory power, right? But the general idea is that if we have this prevalence of driver variables across models, basically we are getting close to the explanations, because good explanations are hard value assertions, right, about reality. The other part is, the take about anomalies and refutations. And the thing is that generally in machine learning, anomalies are treated as, Lakatos will say, monsters, right? They usually say, okay, there's too much variance here. We take these data points out, probably some mistake or whatever. Here we are very comfortable with anomalies. Right? We consider that they have high information content, right? And they are telling us interesting things. That actually, if we look at the group of models and we see no change, maybe the value, the models as providing theory is degenerating. And the protected bell observed here is seen this way, right? It's basically gaining from this variable diversity, right? That is one of the causes of the variation. And at least in machine learning, when we're talking about outliers, it's basically what is overpredicted or underpredicted, right? But in this case, because we are talking about unsamples, we have to have ranges, right? Each model gives us a range. And if we want to be statistically rigorous, right? We can apply analysis of variance and also remove some similarities from the models. In this case, this is a modeling using non-financial variables such as the share of female-male literacy to predict GDP. And this was done before the financial crisis, and Cayman Islands was there an interesting outlier spot. And for this specific study was an important piece of information, right? It was not a nuisance, right? Nuisance. So going back to Lakatos, the idea here is that in our research program, right, we can digest the anomalies, right, and actually turn them into positive evidence. And this is, another example of how a variable will behave in a prediction setting. And someone may think, okay, this is actually a good variable, right? Because it has a stable prediction, and maybe something we should keep in the model, right? Maybe not too much, right? Because it's not telling us anything novel, unless we look at this model here, right? And if we go back and recheck the driver variables for that model, maybe there is something that we are missing. That as a practitioner, right? You will look again, and this applies both for social and natural science, right? There is something we will be missing. Our research program is generating if the successive theories don't deliver model predictions, or if the novel predictions that they deliver turn to be false. Novelty is in part a comparative notion. And here, this is what we can do, right? We can compare different models and look back at the driver variables and know if there's actually novelty, right? So, our conclusions. We have argued that Lakatos take on the methodology of the scientific research programs could be seen as a useful abstraction for the ensemble consensus that is used in genetic programming based hypothesis generation. That the ensembles are in fact offering us theory formulations that can be used as explanations. That this can help us also to understand the causes of relating to the prediction or to the anomalies that we see. And in fact, the evolutionary modeling allows the successful theoretical prediction of restoring novel facts, as Lakatos will put it. And we close with a thought, right, that this whole idea of having things that agree or disagree right, can help us stay, honest, right, and epistemically modest. It's in a way an error correction device in research, seeing things in this way. So with that, I yield to you. Thank you again for